We are going to take what we learned about graphing reciprocals from yesterday's class and now apply that to our trig functions. In our trig unit, we graphed sine, cos, and tan. We didn't graph cosecant, we didn't graph secant, and we didn't graph cotangent. But now that we've learned how to graph any 1 over any function, because that's what we were doing yesterday, saying I can graph 1 over any function by following the steps that we did. So if that function on the bottom happens to be sine, we can follow those same steps and we'll be able to graph cosecant. So what were our steps? Well, we drew the graph of the original function. In this case, we're going to draw sine. And then we'll do all of our steps for the reciprocal using that. So here's our graph of sine, and we're going to graph cosecant right on top of that. So the first thing that we did with our reciprocal graphs were our asymptotes. Vertical asymptotes wherever we had x-intercepts, and a horizontal asymptote at y equals 0 if the graph went up forever or down forever. So for this one, we're going to have a lot of, if we graph exactly on here, wherever we have an x-intercept, we're going to have a vertical asymptote. So there's a lot here in labeling them all. X equals negative 4 pi, x equals negative 3 pi, x equals negative 2 pi, x equals negative pi, and so on. Does our graph go up forever or down forever? No. So we don't have an asymptote at y equals 0. The next thing you're going to do is some points. So if we look on here, we have this point right here, which happens at pi over 2 comma 1. Can you see if you did the reciprocal of that one, you would get the same point. So in fact, all of these points where the y value is 1 are going to stay the same, because 1 over 1 is still 1. And all of these points where the y value is negative 1 is going to stay the same, because 1 over negative 1 is still negative 1 as well. Now sometimes this gets confusing of what to do next, because after doing some points, you were supposed to draw the asymptotic behavior. But right now you might not know, should I go up or should I go down in certain sections? Does it go up on one side, down on another side? Because we don't have a lot of points and we don't have any horizontal asymptote to help us. But if you think about a couple of other points on our original graph, for example, right here, sine of pi over 6 is 1/2. What would happen if I did the reciprocal of your y value, 1 over 1/2, or flip that fraction? You would get the point 2 over 1, so you'd have pi over 6 comma 2. Can you see wherever the y value is 1/2, the reciprocal would become 2. And as a result, for example, in this section, it'll go up like that, and all of these sections are going to be symmetrical. And same thing happens where the y values are negative. And so the blue graph that we have here, with a bunch of arrows going up and a bunch of arrows going down, is going to be our cosecant graph. If we wanted to say the domain of our cosecant graph, well, it's going to be everything except for the asymptotes. How could I write an expression to list all of those asymptotes all at once? X can't equal So I want to write all of those. X can equal 0, x can equal pi, x can equal 2 pi, can equal 3 pi, can equal negative pi, can equal negative 2 pi. And forever, how can I write all of those at once? X can't equal k pi, where k is any integer. Good. And our range, our y values are less than or equal to negative 1, or our y values are bigger than or equal to positive 1. In set notation, this would look like this: negative infinity to negative 1, and then 1 to infinity, with the big U in between for the union, which means or. I'm going to get you to do the next one. I'm going to give you a head start to see if you can graph the secant graph. All right, how did you do? I'm just going to label these. Asymptotes. Guess I wouldn't need to do this one. Off the charts. So the graph looks almost identical to the cosecant graph, just shifted over. Now how would we write the domain for this one? X can't equal, we get tempted to do k pi over 2, right? Because they're all over 2, but that would also include, 1 pi over 2, 2 pi over 2, 3 pi over 2, and we just have the odd numbers. So do you remember how we wrote this, but with a k, odd pi over 2? Because that's what we need. Well, we looked at it in two different ways. So I'll rewrite both ways that we did it before. One way that we wrote it is to get an odd number, if you times any integer by 2, you're going to get an even number. Then if you add or subtract 1 to that, you're going to get an odd number. So one way to write an odd number is 2k plus 1. That will give you all of your odd numbers. Or another way that we did the domain in the past is we said x can't equal, and we pick one of them, so pi over 2 is one of our asymptotes. And what's the distance in between each of these asymptotes? Pi. So if we don't equal pi over 2 and then we add or subtract pi as many times as we want, that will get us all of our answers. Oh, take off tomorrow due to smartboard entry. And for our range is going to be the same as before. Y is less than or equal to negative 1, or y is greater than or equal to 1. So with the cosecant and secant graph, they have followed all of the same rules that we've had with our reciprocal graphs so far. Next, we're going to do the cotangent graph, and the cotangent graph mostly follows the rules. It has one slight difference. So here's our tan graph, already graphed for us, and we're going to want to do our cotangent graph. So the problem is with the cotangent graph, you have one thing that says cotangent is equal to 1 over tan. We have another thing that we know that cotangent is equal to what over what? From your identities. cos over sine. So depending on which one of these you graph, you get different non-permissible values. And what ends up happening in the end is we end up graphing this one instead of this one, and we have one less non-permissible value as a result. So I'm going to show you what that looks like. Whether you graph 1 over tan or you graph cos over sine, you will have asymptotes at all of these x-intercepts. So that rule hasn't changed from before. And this one is going to get very full looking very quickly. And all of these equations for these asymptotes are the same equations of the x-intercepts of sine. Because that's what we're dividing by. Cos over sine, we're dividing by sine. And so all of these x-intercepts of sine are also the x-intercepts of tan, and they all become vertical asymptotes. This is where our graph of cotangent doesn't follow one of the reciprocal rules. According to the graph of tan, if we were graphing 1 over tan, we should have a horizontal asymptote at y equals 0. Okay? But if we were to graph cos over sine, that asymptote wouldn't show up. So what ends up happening is wherever the asymptotes are on the cotangent graph, we actually have a point at 0 there. Because these are the x-intercepts of cosine, and can you see if you wrote cotangent as cos over sine, that wherever cos is 0, cotangent is 0. Does that make sense? That if the numerator, if I look at cos over sine, where cos is 0, the numerator would be 0. 0 divided by anything is 0. So we do have points here where if we were truly doing the reciprocal of the tan graph, that point wouldn't exist. Now, one way to help you graph this is, you know on your tan graph you have this point right here, pi over 4 comma 1. What's going to happen to that point? When I graph cotangent, it's going to stay the same, because what is 1 over 1? Stays the same. In fact, all of these points are going to stay the same where the y value is 1, and all of these points where the y value is negative 1 are going to stay the same. So if you add the point, the x-intercepts where cos is equal to 0, where tan had its asymptotes, and you go across where y is 1 and where y is negative 1 and add those points. Now, try to ignore the black lines. Just think about your asymptotes and your points. In this section between those two asymptotes, does that make sense? So, and we'll get this over and over again. So the cotangent graph kind of looks like a flip of your tangent graph. Wow, that last one's bad. Do that one again. Oh! Okay, here we go. Nice. And there we have our cotangent graph. So again, if we wanted to say the domain of this, well, x can't equal k pi. Our asymptotes are at the same places that our x-intercepts were for sine, so our domain is the same as our domain for cosecant, where k is an integer and our range is everything.